All right, so let's go back to electron configurations now that we have an idea of why the orbitals are listed in the energy that they are listed under, why, for example, the 2s is lower than the 2p. So now we can go back and think about filling in these electron configurations for any atom. I think most of you are familiar with the AufBau, or the building up principle. You probably have seen it quite a bit in high school, and this is the idea that we're filling up our energy states, again, which depend on both n and l, one electron at a time, starting with that lowest energy and then working our way up into higher and higher orbitals. And when we follow the AufBau principle, we have to follow two other rules. One is the Pauli exclusion principle. We discussed this on Wednesday. So this is just the idea that the most electrons that you can have in a single orbital is 2 electrons. That makes sense because we know that every single electron has to have its own distinct set of 4 quantum numbers. The only way that we can do that is to have a maximum of 2 spins in any single orbital, or 2 electrons per orbital. We also need to follow Hund's rule. This is that a single electron enters each state before it enters a second state. And by state, we just mean orbital. So if we're looking at the p orbitals here, that means that a single electron goes in the x, and then it will go in the z orbital before a second one goes in the x orbital. This intuitively should make a lot of sense because we know we're trying to minimize electron repulsions to keep things in as low an energy state as possible. So it makes sense that we would put 1 electron in each orbital first before we double up in any orbital. And the third fact that we need to keep in mind is that spins remain parallel prior to adding a second electron in any of the orbitals. So by parallel, we mean they're either both spin up or they're both spin down. Remember, that's our spin quantum number, that 4th quantum number. And the reason for this comes out of solving the relativistic version of the Schrodinger equation. So unfortunately, it's not as intuitive as knowing that we want to fill separate orbitals before we double up on a degenerate orbital. But you just need to keep this in mind, and you need to just memorize the fact that you need to be parallel before you double up in the orbitals. So we'll see how this works in a second. So let's do this considering, for example, what it would look like if we were to write out the electron configuration for oxygen, where Z is going to be equal to 8. So what we're doing is filling in those 8 electrons following the AufBau principle. So our first electron is going to go in the 1s. And then we have no other options for other orbitals that are at that same energy. So we put the second electron in the 1s as well. Then we go up to the 2s, and we have 2 electrons that we can fill in the 2s. And now we get to the p orbitals. Remember, we want to fill up 1 orbital at a time before we double up. So we'll put 1 in the 2px, then 1 in the 2pz, and then 1 in the 2py. At this point, we have no other choice but to double up before going to the next energy level. So we'll put a second one in the 2px. And I arbitrarily chose to put it in the 2px. We also could have put it in the 2py or the 2pz. It doesn't matter where you double up. They're all the same energy. So if we think about what we would do to actually write out this configuration, we just write the energy levels that we see here, or the orbital approximations. So if we're talking about oxygen, we would say that it's 1s2, then we have 2s2, and then we have 2p, and our total number of electrons in the p orbitals are 4. So it's okay to not specify, I want to point out, whether you're in the px, the py, or the pz, unless a question specifically asks you to specify the m sub l, which occasionally will happen, but if it doesn't happen, you just write it like this. But if, in fact, you are asked to specify the m sub l's, then we would have to write it out more completely, which would be the 1s2, the 2s2, and then we would say 2px2, 2pz1, and 2py1. So again, in general, just go ahead and write it out like this. But if we do ask you to specify, you should be able to know that the p orbital separates into these 3, the p subshell separates into these 3 orbitals.